Now with hardening explained, we can then move on to include hardening in the flow rule. So previously, we have all these established and they will remain unchanged even with hardening. What would change, however, is that now when we take the partial derivative of f with respect to time, we need to take into account that f contains both our Cauchy stress and our hardening parameters. So this would contain naturally two components. We replace this part, partial of f over partial tau, by n, and then we replace k dot by expression, the relationship between a lambda dot and h, and we group these two together into a scalar, so the dot product of two they become a scalar. So here we introduce this new scalar function h is minus of partial f over partial k dot product with h. Then we can write f dot as n dot with the dot product with our stress rate minus h times lambda dot, and this needs to be 0 to satisfy Prager's consistency condition. We can then follow the same procedure as before. We express our stress rate in terms of our constitutive tensor multiplied with the total strain rate minus lambda dot, our plastic multiplier, times m, the direction of plastic flow. We plug in this expression, this whole expression, into our consistency condition, and we obtain such an equation. And then we group the terms on lambda dot and establish an expression with lambda dot in terms of the rest of the components in this equation, and we would get this expression. Note that the only difference between this expression and the expression without hardening is the addition of h on the denominator. Then we can plug in the expression of lambda dot to get an expression of stress rate in terms of total strain rate. So the second term here can be expressed as such, and then we replace the dot product by matrix multiplication. We obtain this form. We can then single out the total strain rate and obtain this within the bracket to be the tangent modulus. The difference between this tangent modulus and the previous one without hardening is only this addition of h. It is also symmetric when n equals to m, and this is the case for metal. So we can then write plastic flow rate as lambda dot multiplied with n, the normal to the yield surface at the point where our stress tensor is located. And this is our associated flow rule for metals. In summary, we have covered the theory of plasticity in a rate-independent format. And we started with the yield condition. There we introduced the von Misew's yield criteria, and we have included for the generality the hardening parameters. Then we have the strain rate and the additive decomposition of the strain rate into elastic and plastic parts. We have the stress rate, and this constitutive law is in rate form. We have the flow rule, which express the plastic strain rate in terms of a scalar multiplier times our direction m. M in general is obtained from the plastic flow potential G, but for our purpose in aerospace, for the case of metals, G equals to F, we have associated plastic flow. For the hardening parameters K, they evolve together with our plastic multiplier lambda. And this relationship H needs to be established experimentally or based on assumptions. We have the loading and unloading conditions on our plastic multiplier. These are the Kuhn-Tucker conditions. And based on these conditions, we can obtain the Prager's consistency condition for the case where our yield condition is satisfied and our plastic flow is happening. Based on this condition, which means that F dot equals to 0, we can then derive the expression of our plastic multiplier, and we can use this expression to establish the connection between our stress rate and total strain rate. And this connection, which is the tangent modulus, is symmetric for associated plastic flow, which is the case for metals.